Question 4. So part A says a photon has a wavelength of 624 nanometers. We need to determine the energy of the photon in electron volts. Okay, so whenever you're given the wavelength of the frequency, the formula that needs to come to mind is Planck's formula. Okay, so in terms of wavelength, this is the way it comes out. In terms of frequency, we have a product of Planck's constant and the frequency. Okay, so let's plug in the values. Planck's constant is 6.626 by 10 to the power negative 84. The c, which is the speed of light, is 3 times 10 to the power 8 divided by the wavelength 624. Now nano means times 10 to the power negative 9. In other terms, we are dividing by that. Okay, so we can now determine the energy. So I'll start with the top, 6.626 by 10 to the power negative 84 multiplied by 3 times 10 to the power 8 and then divided by 624 times 10 to the power negative 9. 10 to the power negative 9. So the answer I'm getting for the energy there is 3.18 times 10 to the power negative 19. So that is in joules as our energy. Okay, and then we can now move to B, but before that we have to convert this to electron volts. So the conversion factor, 1 electron volt is equal to 1.602 times 10 to the power negative 19 joules. So you can put x here to represent the volts. So we're just going to divide by that value. Okay, so divide by 1.602 times 10 to the power negative 19. Okay, so that's giving me a value of 1.99 okay, electron volts. Okay, so that's how you deal with this conversions. And then if you look at B is asking us to calculate the wavelength, okay, where we're given a transition, okay, in the hydrogen atom. So, and then we're asked to determine also what the type of electromagnetic radiation is emitted, given n is equal to 3 and n phi is equal to 2. So calculate the wavelength of light emitted when each of the following transitions occur in the hydrogen atom. So in this case, it's a two-way thing. Since the question is so general, we have the transitions, and then we've not specified which one is the final and which one is the initial. Okay, so I'll consider one case where we are saying we have a transition from the second to the third, right? Okay, so where we have an electron moving from the second energy level to the third energy level as our final. So the first part is to determine the wavelength. So whenever you are determining the wavelength from transitions, the formula that can help you very fast is we call it the Rydberg equation, which is 1 over the wavelength, and then the Rydberg constant in meters is 1.097 times 10 to the power 7 meters negative, and then in the brackets you have a transition, so 1 over the initial squared minus 1 over final squared. So you just plug in. So 1 over the wavelength is equal to 1.097 times 10 to the power 7 meters negative, and then The initial we are taking to be 2, and then the final we're taking it to be 3, right? Okay, so for this transition, what do we expect? So 2 squared is 4, 3 squared is 9. So we can simplify that. 1 over 4 minus 1 over 9, 5 over 56 multiplied by 1.097 times 10 to the power 7. Okay, so we have 1 over our wavelength being equal to 1523611.1 meters negative. So we can make wavelength the subject. So our wavelength, since it's in terms of reciprocal, we can just divide 1 by whatever we have. Okay, so after dividing, the answer I'm getting, is, in terms of scientific notation, is 6.563 times 10 to the power negative 7 meters, because we used our constant in meters, so the wavelength is also in meters. Okay, now we've just calculated the wavelength. The other part of the question is asking us to, so by the way, you can also try the reverse. Since this is the transition we've assumed from 2 to 3, you can also try 3 to 2, you see what you're going to get. So I think the difference in terms of energy would be more on the sign, but you can try that as well and see the wavelength you're going to get. Expect the same answer. Okay, so we've determined the wavelength. Now, what type of electromagnetic radiation is emitted? What type of electromagnetic radiation? So usually we deal with the 3: infrared, and then visible light, of course, and UV. So you have to choose which one it is. So to help us to make this easy, the visible light is categorized between 400 and 700 nanometers. Okay, and then you know that UV has got a half frequency compared to the infrared. So this side, from the left to the right, there is an increase in frequency. So it's supposed to be the opposite for the wavelength. So UV has got a shortest wavelength if you compare the 3. So EA meaning that it's supposed to be less than 400 nanometers, and then the infrared is supposed to be greater than 700. So we're dealing with nanometers here, so it's better we convert the answer we have to nanometers. How do we do that? Since it's meters, we can just multiply by 10 to the power 9, right? So if I multiply by 10 to the power 9, the answer I'm getting is 6.56 times 10 to the power 2 nanometers. So assuming our calculations are okay, and looking at the value we have, if we can have it in normal, we can have a value of about 656.3 nanometers. So looking at this value is between 400 and 700, so we would conclude this in visible light. Okay, that's what we would say. If it was going to be greater than 700, we would say it's infrared, and then if it was going to be less than 400, we would say UV. Okay.